My name is Stuart Marks. I'm an engineer in the Core Libraries group working on JDK. And this talk is about OpenJDK testing, and in particular the pitfalls of OpenJDK testing. So I'm going to assume that you have some background in what the tests look like in OpenJDK and some basics already. I hope you've seen some of the presentations my colleagues have given that are an introduction to testing in OpenJDK. So this presentation is about pitfalls that can arise in testing, and it's really going to be example driven. So there are going to be a lot of example tests and test code in this presentation. And so with that introduction, I will dive right in. So here we have an example test. It really doesn't do anything interesting, but the point of this is to look at the test tags at the top. So in the comment at the top of the source code, there is @test, which marks this file as a test. And then there's a summary line that describes it. There's nothing interesting going on here. We've added a third tag. Suppose we've modified the test to have a dependency on some class named another class. And so we need to add a tag @build another class that tells the JTREG test framework to build that other class. All right, well, that seems pretty simple. We've added an @build tag. What could go wrong with this? There's some description here of why that previous test introduced a bug. There's a rule in JTREG. The tags that appear at the top of a test are kind of a little programming language. And there's a rule that says if there is no run action, then an @run main test class, or whatever the name of the class is, @run main is assumed if there is no run action in those tags. So if you were to look back at the first example, there was no run action, and so it assumed that @run main was there. In the second example, there was an @build tag. It turns out that @build is actually shorthand for @run build. Putting an @build tag into the test actually does have an @run action. So that means that this implicit behavior of having an @run main tag is no longer invoked. So the @build counts as the run action, and so that default behavior does not occur. So what happens? What JTREG does is it finds this test. It says @build another class, and so it goes and builds it. And since there are no more actions in the tag language, it simply does nothing. So really the problem with the test code, it does some compilation, but it does not actually run the test. And so that's a very surprising outcome for having added an @build tag. What is necessary here is to have an @run tag that tells JTREG that, yes, you really do want to run the test. What I've adopted for the test that I've written, a rule that is every test must have an @run tag, even if, strictly speaking, it's not necessary. So now in recent versions of JTREG, this change was put into the open source probably, I think, in April of 2013. There's a new rule that says that the last run action must not be a build action. In fact, if the last action turns out to be a build action, then JTREG will now consider that to be an error. So the example on the previous slide, where it would actually not run the test, that would actually be considered an error by JTREG now. There may be builds of JTREG floating around that still have the old behavior, so that's something to look out for. If you've grabbed a build of JTREG, it still might have this behavior, and you might inadvertently write a test that doesn't actually run because of the way you've set up the tags. So my recommendation there is to get the latest JTREG sources and build them and use that version of JTREG so that you can make sure that you don't fall into this pitfall. So what I have here is an example of a shell script test. This is an actual shell script from the JDK source tree. For brevity, I've taken out the copyrights, but this is copyrighted. There's an @test tag, an @bug tag that identifies which bug this is a test for. And then there's some shell script syntax here, which gets the operating system name and puts it into the variable OS. And then we have a shell case statement. What this does is it says for certain operating systems, it assigns the PS and FS variables. So PS is path separator and FS is file separator. So you can see for the Unix-like systems, we use colon and slash for that. Cygwin is a special case where we use semicolon. On Windows, we have PS and FS be set to the characters that are appropriate for Windows. And finally, we have a default case that says if it's not any of the Linux or Unix systems or Cygwin or Windows, then we don't know how to deal with it. So we error out with an unrecognized system. We have the logic of the test. It's using the FS and PS variables in the appropriate places when it needs to construct path names and actual paths like the class path. If you read through this very carefully, you can see it's compiling some Java source files and adding some directories to the class path. And then it's removing some temporary files that might have been left over from the previous test run. And then it's running the Java VM on the test file that was just compiled, and it's passing it the argument word first, and then it invokes Java again the second time on the same test file and passes it the argument, which is the word second. Well, that's pretty messy, so let's discuss what's going on here. The first two slides was really assigning variables based on what operating system, so that the path variables and the path separator characters could be used properly depending on what operating system was in use. Actually, it's unclear whether this is still necessary. It might have been true on old versions of Cygwin or old versions of other support systems that gave Unix-like behavior on Windows systems that were very sensitive to having backslashes versus slashes in the path names. But in fact, this is no longer necessary. If you took all that stuff out and just used slash and colon, then the test would probably continue to work. Nonetheless, you will find this sort of the case statement over the operating system and the assignment of path separator and file separator variables. You will find that at the top of many shell scripts. Using those variables in the path names makes the script very hard to read. Instead of the colon or slash separating path name elements, then you have this variable interpolation in there. It just makes it very difficult to see what's going on in the actual logic part of the script. But more importantly, if you set aside the syntactic noise introduced by those variables, there are some more serious problems with the test. Specifically, the test first compiles a Java class using the Java-C compiler. The problem is, if there's a syntax error in the file, I mean, that shouldn't occur, but it's possible if somebody's editing the file, they might introduce a syntax error, or the class path might be wrong and it might be missing a class, or one of the variables is wrong, or something. There are many reasons that a compilation can fail. Well, the problem is that it doesn't actually handle errors at the compilation step. Now, Java-C will certainly emit some error messages and return an exit status that is not 0. But the shell script does not do anything with that, and so the shell script will just charge ahead. It might or might not fail when it tries to execute that class. Now, if there's an old version of the class that happens to be left over from a previous test run, it might go ahead and execute that instead. So you might actually have a compilation error and execute an old class file, and the test will pass even though there was a compilation error. So that's a pretty serious problem. There's another problem with shell script test, which is that the way JTREG gets the pass or fail information from a shell script test is it looks at the script's exit status. It's possible in writing shell script to set the exit status explicitly by using the exit command. But what this shell script does is it relies on a subtle feature of the shell script, which is that the exit status of the script is the exit status of the last command in the script. What this test does is it actually invokes the Java test class twice. First with an argument of the word first, and the second time with the argument of the word second. Now suppose there was a problem with the first invocation of the test. So that might emit some error messages, and it might return an exit status of non-zero. But then the shell script would just go ahead and execute the second test pass, and if that succeeded, then the entire test would be considered to have passed. And so what that did was that covered up the failing exit status from the first part of the test run. And so that's another serious problem. This kind of shell script technique is actually very fragile. Suppose I were editing this and I wanted to add some debugging output, or I just wanted to add a message like an echo command, and I happen to put that at the bottom of the script. Well, because of this shell script behavior of the exit status of the script being the exit status of the last command, if the last command is echo, well, echo actually always returns success. I've never seen the echo command return failing exit status. What that means is that JTREG will get an exit status of success based on the echo command, which is the last command in the script. And regardless of what happened when the script executed the Java commands, if those passed or failed, that would be ignored by the shell script, and the shell script's exit status would always be success because that was the last command in the script. Relying on the shell script behavior of the last command's exit status determining the exit status of the shell script is very, very fragile. So my recommendation there is to make sure that the exit status of the shell script is always set using an explicit exit command. This is a shell script called Test Serialization Mismatch. This is a draft of the test based in January 2013. This test has since been rewritten in Java. After looking through this shell script test, you'll be able to see why. There are many, many problems with it. But first, let's just look at the source code of the shell script. We have an invocation of javac, and it compiles some Java source files, and these are for the client part of the test. And then the next line is another invocation of javac, which compiles the server part of the test. Just below that, now we have a fairly complicated command that invokes the Java virtual machine, and it adds the server classes to the class path, and then invokes the server class. So here what we're doing is we are starting up the server side part of the test. Now, it puts this command in parentheses and redirects the output to a file called URL path. The variable URL path is assigned earlier in the script. It's not actually shown here, but it's pointing to something valid. So we redirect the output to the URL path file. That includes both the standard output and standard error from this invocation. Put that into the background, and then take the process ID of the server process and put that into a variable called serverPID. The next thing we do is we go into a while loop where we wait for the URL path file to become present, and that's what the -f test in brackets does. When that file is present, we break out of the loop. Otherwise, we sleep for 2 seconds and try again. Then, once the file is actually present, we read a line of text from the URL path file and put that into the variable called JMXURL. Here what we do is we run the Java VM on the client side of the test, and we wrap this in parentheses, redirect the output, and pipe all of that into grep for a particular error message, which is severe, failed to fetch notification, and so forth. So we grep for that error message, and then, if you look very carefully, this is all inside of the shell backquote syntax. So it takes the output of that Java pipe to grep and puts that into the hasErrors shell variable. Once we've done that, we kill off the server process, and then what the test does is it tests the hasErrors variable, and if it is empty, that is the -z test in the if statement, hasErrors is empty, then we consider the test to have passed. And if it's not empty, then we consider the test to have failed. We echo the output of hasErrors, and we exit status 1. Following my previous recommendation, this shell script provides an explicit exit status in all paths through the shell script instead of relying on the exit status of the last command in the script. But there are a whole bunch of problems in this test, and so let's go over them one by one. So what this test is trying to do is it needs to compile 2 separate incompatible versions of what is essentially the same class file. That's really what the test is trying to test. It wants to put these different versions on, one on the client side and one on the server side. It's difficult to do this with JTREG compile or build tags, because those basically really want to compile something only once. It's very difficult to have 2 separate versions. So instead, the author of this test decided, okay, well, since we can't use JTREG build tags to do that, then what we should do is invoke the compiler explicitly using a shell script and have the compiler run javac and compile those classes for me. So similar to the previous example, there's a problem, which is, what if the compilations fail? That's not tested for at all in the shell script. Subsequent parts of the script, when they go to invoke the Java VM, they might fail at that point, but they might not if they happen to find some old version of the class lying around there. The compilation steps, if they fail, do not cause the entire test to fail. So that's one problem. There's another problem, which is kind of a small thing, but there are a bunch of variables put into the environment by JTREG, in particular test Java and compile Java. Test Java points to the JDK under test, whereas compile Java is the JDK that is actually being used to run JTREG itself. And so really, if you're compiling things, you want to use compile Java because that is a known good JDK as opposed to the JDK that is being tested, which is in test Java. The shell script is actually compiling the classes with the wrong version of Java. It's unlikely to cause a problem unless there is a bug in the compiler, but still, it's using the wrong JDK, which could possibly result in some strange errors if you're not careful or if there's something strange in the environment. First thing that the shell script did was to start up the server, and then there was a while loop where the client had to wait for the server to start. So that's why we have sleep inside of a loop here. But there's actually a race condition here. So the URL path file is not created by the server. It's actually created by the shell that's running the shell script. And then the JVM running the server code is redirected into this pre-existing file. So what happens is this while loop is actually always going to terminate immediately because the URL path file will have been created immediately by the shell even before the server has started running. So the problem is there's a race condition where when the client wants to read the URL that was supposedly written by the server, it might encounter an empty file. So there's a race between the client and server where the server is going to write the URL into the file and the client is trying to read it. So the client might have tried to read it before the server actually wrote it. But there's another problem, which is that the way the shell script is written, if the server, for instance, has exited with an error, or if there's something else going on the server where the first line of text in the file is not actually a URL, well, the read command from the shell is only going to read the first line, and what it reads might not actually be a URL. So the client might try to connect to something that it thinks is a URL, but is in fact garbage. That's another problem. The way the client is run, suppose the client throws some unexpected exception. Well, the client's output is piped through grep. The grep pattern is for a specific error message. And if that specific error message is not present in the client's output, the output will be empty and the test will be considered to pass, even though the client might have thrown some entirely unrelated exit. So this is an extremely serious problem. If the client fails, then it might emit some error message that will be thrown away by the grep command, and then the test will test the output, find it empty, and consider the test to have passed. The test reports pass even though the client actually failed, and worse, we've destroyed information about why the client failed, because that's thrown away by grep. This kind of test, it's possible for there to be failures or errors in this kind of test. You might have automated test cycles that run this test frequently or even continuously, and it might be failing, and you'll never know even if somebody goes to look at the test log, because the test framework is always getting an indication of pass from this shell script. Another issue is that the exit status of the client is not checked. Since it's in a shell pipeline, it's actually kind of hard to get the exit status of something that is earlier in a shell pipeline. So that's more information that's thrown away. It's very fragile because the grep pattern is a very, very specific error message, and the client might fail because of some other kind of error message, or actually the system might change, or the system might be localized so that the proper error is coming out, but in fact the error message might be different, and so that would cause the test to misbehave as well. You can see that there are a lot of problems that arise when writing shell scripts, and so much so that my recommendation is simply to avoid writing shell scripts. It seems like it ought to be easier to manage subprocesses using a shell script than in Java, but that's not really true. We had some logic in the previous shell script that forked one subprocess and then wanted to wait until a particular event occurred before forking the second one. Well, that's actually pretty hard in the shell script, and you can see that there was some logic that attempted to do that in the example, but it had some problems with it. Worse, suppose we wanted to wait and retry periodically every 2 seconds. We wanted to avoid waiting for, say, more than 30 seconds. So we'd have to add a bunch more logic in that while loop to make sure that we didn't wait too long. If a command inside that while loop were to hang, we might never break out of that while loop. There are actually quite a number of subtle behaviors and difficulties in trying to do things like timeouts using shell scripts. In Java, if you were to try to manage subprocesses, there is a set of process libraries in the JDK already, java.lang.process and process builder, and those are pretty low level. It's actually pretty difficult to manage subprocesses using those. So what's necessary is some kind of higher level library that deals with certain issues of managing subprocesses from Java more effectively. And so what's happening is that certain areas of the test suite are developing test libraries that are shared across a bunch of different tests that encapsulate common functionality. For example, in the RMI tests, there is something called the RMI test library that has a bunch of utility code that manages subprocesses. Now, these are not very general in that they are managing RMI-specific subprocesses, but the techniques in use here could eventually be generalized to manage subprocesses and thus replace the subprocess management that one would like to do from shell tests. Especially in tests that want to do client-server communication, there are a lot of shell scripts sprinkled around the test suite that use fixed ports for communicating between a client and a server. And this is a problem. If somebody else happens to be using that port, then the test will fail unexpectedly and also intermittently. Now, this test in particular happens to choose a random port. That's actually in the server code. But what it requires is that the information about which port is being used be passed from the server to the client. The way that this shell script did that was by trying to communicate between the server and the client through the file system. So the server has to tell the client where to connect to it. And the only way to do that in a shell script is kind of through the file system. So that's why there's this very clumsy redirect the output to a file, test if the file is there, read a line from it, and so forth. If you are writing this test in Java, then you can manage the server and the client using the Java programming language. And then if they were inside the same JVM, then you would just pass things like the unique port number directly to the client. If the client were using a subprocess, then the JVM could simply pass the port that the server was using through a command line argument or through a pipe or something like that. It turns out that using Java, there are many more effective ways to pass information between a client and a server, like a unique port number, instead of using this very clumsy mechanism that shell scripts use. So one of the things that we do need to do in the JDK test suite is to develop more and better test idioms and test library support. In particular, one of the things we do need to do some work on is to call the compiler from Java programs. So we've seen a couple shell script examples where the shell script itself invokes the JavaC compiler. Turns out that it is possible for Java programs to invoke the compiler. For instance, the JSR 199 is a compiler API where you can get very fine-grained access to the code of the compiler itself running in this JVM. It's also possible to simply invoke the compiler's main method and pass it an array of strings, just as if those strings had been passed to JavaC in the command line. I believe it actually runs JavaC, in that case, in this same JVM. So we avoid some fork and exec overhead, but we get the additional advantage of running the compiler in this JVM so that we can have complete control over what it's doing and catch exceptions and compare its exit status and so forth. There are large areas of the JDK that have specialized needs from a testing framework. In our environment, we developed that specialized code to do that kind of within a testing library that is specific to that subsystem. The examples, for instance, are JMX or RMI. They have their own test library that supports specialized needs, and this technique needs to be pursued and evolved further. I'd also recommend that such frameworks try to figure out how to use kind of a white box style testing instead of black box testing of testing the output. So if you look at a shell script, it can't actually go inside the JVM. So the only thing that it can do in this case is inspect the output. In this case, it is trying to find a particular error message. For a variety of reasons, that's quite fragile. If this test were running inside the same JVM as the client, then what it could do is it could use some internal interfaces into the class library to examine the state of what's going on and get a much more precise indication of whether the test passed or failed. So it is possible to rewrite shell scripts in Java, and they become much more robust and reliable. This shell script test was actually rewritten in Java, and this was checked into OpenJDK in May of 2013. And the Java code that re-implements the shell script is somewhat verbose, but it is much, much more robust. And it's actually fairly easy to read. The shell script logic for capturing output and pipe and grep and capturing process IDs and killing things and so forth, killing the server subprocess, is actually fairly subtle and it's easy to get wrong. And in fact, as we've seen, this shell script does get it wrong quite a bit. The rewritten version in Java should be much more robust. It is somewhat more verbose, but actually it's quite easy to understand, should be quite reliable. I'd like to conclude with some issues for discussion. The test suite in the JDK is a work in progress, and there are a lot of variations in behaviors across the different tests. Different people have different opinions about what tests ought to do. A lot of this needs to be discussed and some decisions need to be arrived at. Over the history of the JDK, different engineers have written tests in different styles and they behave inconsistently. These are some things that need to be cleaned up. There's an open question of whether tests should clean up after themselves. We saw in a couple examples here tests that created temporary files. Some people like the idea of if a program creates a temporary file, then that program should be responsible for cleaning it up. And that makes a certain amount of sense from a cleanliness perspective. On the other hand, the JTREG test framework will automatically clean up any files that the test happens to leave in the scratch directory. So since JTREG does that cleanup, then maybe we don't need to have that logic inside of every test that creates a temporary file. An additional point about relying on JTREG to clean up temporary files is that if the test were to clean up temporary files for itself, if the test encountered a problem, then there might be some interesting information in those temporary files that might be useful for debugging that problem. But if the test were to clean up those temporary files itself, it might destroy that diagnostic information. And so JTREG can be instructed not to clean up temporary files. Somebody developing those tests can go and look at those temporary files left around after a test run. Those might be helpful in diagnosing problems. Somewhat related to the idea of cleaning up temporary files is whether tests necessarily need to be runnable in a standalone fashion or whether they can rely on having been run by JTREG. So historically, all of the tests start by invoking the main method of a class, which is very easy to invoke from the command line. There are certain things like the behavior of JTREG and build tags and run tags and so forth that really start to make the tests rely on JTREG. Potentially this notion of JTREG cleaning up temporary files, that's an additional reliance on JTREG. What's clear that is necessary is we need to develop test libraries for certain subsystems, such as JMX and RMI. And so those test libraries have a lot of logic that is specific to tests in those areas. But if you were to try to invoke a standalone test, you have to do a lot of typing to put the library into the class path and so forth. And it just makes it much more cumbersome to run tests in a standalone fashion if you have test libraries in the picture. And so JTREG does this for you. That's another point slightly in favor of just relying on JTREG instead of holding on to this notion of running tests in a standalone fashion. Another issue that needs to be discussed is how verbose should tests be? There are certain test frameworks, such as JUnit, which are pretty quiet if tests are successful. And that's nice, and there's something to be said for that. In the JTREG tests tend to have a style of being more verbose, in particular emitting lots of messages even if they passed. And I think the reason there is that it's a little too easy for a test under JTREG to miss a case or to accidentally report success when it really failed, as we've seen in some examples here. JTREG only really looks at the exit status of a test. For instance, if you have some subtle logic in a test, if you might miss a case, if your test's main method happens to exit normally, well, JTREG considers that to be success. And so even if something bad happened in the test and you emitted error messages and so forth, JTREG might still consider that to be success. The style that I've pursued, and several of my colleagues have also pursued, is to be fairly verbose even if the test is successful. That way somebody can look at the test log and say, oh yes, it executed the test, it tested a particular case, and it did so successfully. If that's not present in the log, then you kind of have to go read the source code for the test to figure out whether it actually was testing anything properly or whether there might be a logic error in the test where it might have skipped the test. Occasionally, somebody will make a suggestion that a test have something other than a Boolean output pass or fail. In particular, a test might look around and see, oh, well, there's something wrong in the environment, like there's not enough memory or file system space on the test. And somebody will suggest, oh, maybe the test should issue a warning that there's a problem with this system or something like that. Well, the problem is that JTREG really only collects a Boolean from the test, pass or fail. It does collect a bunch of error output, but if you were to issue a warning from a test but still have that test indicate passing, then that warning might end up in a log file somewhere, but probably no one will ever see it, because no one ever looks at a test log file if the test said that it passed. Warnings from a test that do not cause failure are really not very useful at all. If there's something wrong, my recommendation is that the test indicate failure, even if it's something that you might not consider to be an ordinary test fail, because issuing warnings and having the test pass is just not going to be useful. In an ordinary test run, there might be thousands of tests, thousands of test log files, and warnings buried in there are never going to be seen by anybody. So that concludes my presentation. There's lots of interesting issues raised here, some things that could be discussed, and further discussions that would be had in the future. And so if you're interested in discussing any of these issues, please tune into the Quality Discuss mailing list at openjdk.java.net. Thanks very much for listening.